Howdy guys, this is Mr. Russell. Let's talk about the scientific method. So you're going to want to look on page 2 of your notes to find this. That's the Unit 2 notes. So if we start, we are going to take a look. Try to point out the logical fallacy or error in this cartoon. Okay, it's just a cartoon, so I understand it's not the best scientific example, but I hope you can understand that there's a logical fallacy in her thinking where she thinks that only skinny people live in Colorado. Well, so if you move to Colorado, you must be skinny. Well, that may not be the truth. So the way we get around these logical fallacies and try to not commit those is using the scientific method. This is a tried and true method used for hundreds of years, and this is the real hallmark of science and how it was able to develop. So it starts by observing something and then coming up with an idea. And then a person formulates a hypothesis, and then they must test that hypothesis. Now, and then we go into the revise reject phase. We have to understand, like, did we really answer the question? Did we answer it to the fullest effect? And what we try to do is we go back and reformulate the hypothesis again. Now, this is what most general run-of-the-mill scientists do every day. And they're working through their entire lives going through this whole process. Only then when they make a breakthrough, see, that's what that's why we call it a breakthrough, then and really get onto something good, then it starts to become a theory. So this is most of the work that happens. So a hypothesis must be measurable, it must be observable, and it must be objective. It is done it's in the form of a statement, usually an if-then statement, and it's not an opinion. So a good example is if a higher concentration of vinegar is added to iron, it will rust faster in a certain amount of time. Okay, so that's a good hypothesis, just a statement. This will happen if this happens. Now, a research question is very similar to a hypothesis. But it's just in the form of the question. Now, it contains the independent and dependent variables in it exactly. Sometimes it can contain a control variable as well. So it says, to what extent does the concentration of vinegar applied to iron have an effect on the mass of rust in a given time period? So there's subtle differences to them, but they're essentially the same thing. Now, this is one of my pet peeves, is when somebody says they have a theory. I've got a theory how this works. That's probably not what they mean. They mean that they probably have a hypothesis or an idea. So theories are not hypotheses. A theory's been tested, and it's the working model of what we understand is happening. Like the theory of relativity, it's been tested, but it's not become what we know as law yet. So the experimental design, when you design your experiments, you must know these important vocabulary words, especially for your test. So an independent variable is also known as the manipulated variable, and it's the factor that's changed during an experiment. It's the one that you change. And now the dependent variable is the respondent variable, and it's the quantity that's being measured during the experiment. So you change the independent variable, and you are measuring the dependent variable. Now, a control is a good thing to throw in there. Control is a point that's put in there that doesn't receive the independent variable. For example, if we were measuring the pH of water, that was our dependent variable. Well, then I would want to put in something that I would want to put, I'm sorry, not the pH of water, the pH of acid. If I was measuring the pHs of different acids, I would want to put in water because water would be my control. It doesn't have any acid in it. And just to see how water affects that, because there is a lot of water in acids. And then for a constant, all conditions are kept the same. during the experimental group. The best constant is probably temperature, pressure, um, a couple of other things. Volume of substance added, the equipment, the people running it. We want to try to keep everything as constant as possible so that we can really see a difference between the independent and dependent variable. So a qualitative, there's two types of data. There's qualitative data and there's quantitative data. Qualitative has to do with observations. It is any data gathered any non-numerical data gathered. And then quantitative is any numerical data gathered. So I don't have that written down but on the screen. But this is non-numerical, and then this is numerical, all right? Or meaning number. So the solution has a temperature of 24.8 degrees Celsius. Is that quantitative or qualitative? Well, it has a number on it, so that's going to be quantitative. All right. Now the solution in the 250 milliliter beaker has a blue tint. Well, that's kind of a trick question. It's actually going to be qualitative. Even though it has a number in it, the number does not describe the observation. Okay. It's just in that certain beaker. It could have been in any kind of beaker. You could have cut this out and you would have still gotten qualitative. So that was just kind of what we call a red herring. Now when we draw a graph, important things to know about a graph. So you may have heard of dry mix before, D-R-Y-M-I-X. D stands for dependent, responding, and y-axis. And then M stands for manipulated, independent, x-axis. So this is how I remember which one's on which axis. So whenever we graph something, it always has a title up here, and an easy title to put down is going to be the y versus x, whatever's on the y-axis versus whatever's on the x-axis here. So let's go ahead and do a mastery check. Which question cannot be answered by experimentation using a scientific approach? A, does hot water freeze faster than cold water? B, will wearing a copper bracelet reduce arthritis symptoms? C, do roses smell better than carnations? D, will popcorn kernels soaked in water produce a greater volume of popcorn than dry kernels? All right, hopefully you pick C, because C is an opinion, okay? It doesn't have, it's talking about smelling better, and that's an opinion on based on the person. So you would have to rephrase that so that do people prefer carnations better than roses? You could maybe test that. That would have some numbers on it. Which of the following hypotheses could not be tested using scientific means? A, if humans lack sleep, then their attention span decreases. B, clownfish are afraid of dolphins. C, aspirin is more effective at curing headaches than ibuprofen. Or D, students at BHS prefer paper towels over hand dryers in the restroom. You should have picked B again because, or B, because it is, again, an opinion. You could not test how another creature feels. That would be extremely difficult to test. What emotions that clownfish is actually feeling. Do the clownfish feel afraid? Who knows, right? So we'll have to check that out. All right, have a great day.